So this is our ME1301 final project by Aaron Met and Carl Met. Our project goal was to create a robot that can follow the line of a closed loop track, mark the location where the robot entered the track, and then follow the line around until it gets back to that location, and then report the length of that line. So our group broke this down into one category for each one of these tasks and how they can be accomplished. And our overall design philosophy was to keep it simple because less sensors, less motors, and other components, moving parts, means that there's less problems that are likely to occur. And we also tried to uh, use components for accomplishing more than one task, which I'll kind of explain later. So to find, follow, and track the line, anything dealing with the line pretty much, photoresistors were used. The photoresistors could detect black and white. They really just detect the intensity of any light that's hitting them. We also used them for detecting when a wheel spoke went past the sensor. And this keeps it pretty simple because these three systems both use the same type of sensor, which we are fairly familiar with, and we were able to easily troubleshoot, not have to worry about using more than one type of sensor. And the less different types of components you use, the easier things generally are to troubleshoot. So for driving, the main requirement for the drivetrain is that it just has to be able to move forward and turn the robot in either direction. And the turning is pretty important because you want that to be pretty consistent and reliable, and it has to turn easily and simply. And this was really just done by using two independently powered wheels that could move at different speeds or even different directions from each other. And then the front had a ball roller for low ground friction. This ball roller just gave it a third point of contact and low friction on the ground so that it could easily turn. And it had even weight distribution on both wheels, so they had equal traction. And then this is pretty simple along with our design philosophy because the wheels are the only moving parts and the only things that need to be controlled. For marking the line, this was done using a servo with a paper clip on it as a hook. When it detected the line and followed along it for a little bit, it would stop and drop the marker, the strip of cardboard, and once it came around the track, when both photosensors detected black, that's when it knew it stopped the track. It was done completing it, and it would display the length of the track. For the control algorithm and drive cycle, so this basically started when the robot was inside the track, and the robot would just drive straight until it detected one sensor, and then it would drive towards that sensor. So if it detected the right sensor, it would turn to the right so that the line was in between both sensors. And then it would follow the track for a few seconds, and then the robot would place the track marker, and it would start the tracker counter. It would count when each spoke goes past, which was on a different board. You would just send a signal to that to get it to start. And then the robot will follow the track, and then it'll move. Every time it detects a sensor, it'll move away from that sensor so that it stays going along the track so that the line is between both sensors. Then when both sensors are triggered, this is almost probably 99% chance to be when the tracker strip is detected, when you have that black strip going across the track. And at this point, it'll tell the tracker to stop counting spokes, and then it'll display the track length on the screen based on the number of spokes that it's counted. And here's a video that graphically depicts the line following process. Okay, so at this point, the robot has just driven forward, and you might have seen it turn to the right a little bit. and that's when it found the track and it knew to turn over and line up with it. Now it's following it for a little bit, and at that point it just stopped. That's the point when it will deploy the stop strip, and it'll also start the tracker, tell it to actually start counting spokes. And now the robot's just going to follow along the line until it gets back to the start again. And at that point the robot detected black on both sensors, and it stopped moving, and it also told the tracker to stop counting and report the values that it collected, which doesn't actually work in that video or in that specific test that we recorded, but it obviously worked in our demo in class. So a few problems we encountered. The main problem was the friction on the track. Our original design didn't use the ball roller, and we thought it could slide fairly well on those sensor tubes, but we were wrong. We decided that it wasn't turning consistently enough, and it was taking too much power to get it to turn, and then it was bouncing, and it just wasn't working out well. So we put a ball roller on there, and that improved things a lot. And then we had problems with the voltage drops on the Arduino board when the motors would run. Analog sensors are they detect the voltage that's created on the circuit due to the resistance, the change in resistance. And so if the voltage drops due to another load on the circuit, it'll think that the sensor is reading something, and this just causes bad analog readings. So we decided to run the wheel sensors on a different Arduino, because that would draw a more consistent load, because all it was running was those wheel sensors and the LCD. And then we had a few problems with wiring connections. We had a bad wiring connection to one of our photoresistors, and we believed for a while that it might have been a bad photoresistor, because we rewired it, we replugged everything, retaped it, made sure no wires were touching each other. We still had problems, but then after a few more times trying it, it ended up somehow working again. So we're not really sure what happened there. We tried changing the batteries, but it had to have been a bad wiring connection that we didn't find the first time. So some improvements we could have made: we could have used a separate power supply for the servos. The servos drew a lot of current, and they affected the analog readings at some point. So there is a possibility we could have gotten it down to using one Arduino board had we supplied separate power to the servos, but we decided against that because we didn't want to make it too complicated, and didn't think we would have enough time to get it working. And then we thought of using a digital encoder, rotary encoder, for tracking instead of the photosensors. This probably would have been more reliable and not as sensitive to voltage, because a digital encoder just detects either like basically 1 or 0 when the pickups on the encoder go past, and it's a lot better for this application, more consistent. And then the other thing, the main problem we had in our demo was that the sensors were too far apart, and our design wasn't as suited towards the tight track that we had, the tight turns on it. So if those sensors were closer together, it probably would have picked up more finely on those curves and been able to follow the track with more precision, and it wouldn't have missed the track and had to turn too quickly. So overall, our project was mostly a success. Had it been on a wider, less tight turn track, it probably would have done a lot better. Probably would have completed the goal just fine. And yeah, we learned a lot doing this project, and a lot of troubleshooting, and it really made us think about how to do stuff like this in the future. Thank you.